Welcome to this explainer. Okay, so today we're talking about an invisible, completely existential threat that honestly surrounds us every single day. I'm talking about electrical faults. We rely on electricity for literally everything, but when a wire frays or a component breaks down, all that incredible invisible energy, it needs somewhere to go. And if we aren't careful, well, it goes right through us. That is exactly why Section 5 of the AS/NZS 3000 2018 wiring rules exists. It's our ultimate safety net. It is the literal groundwork that keeps our homes, our workplaces, our families safe. So today, we're going to unpack the anatomy of this lifesaver. Let's get into it. Right off the bat, Clause 5.12 of the standard sets the stakes with this fundamental requirement. I want you to listen closely to these words. Enable automatic disconnection of supply in the event of a short circuit to earth fault or excessive earth leakage current through protective earthing arrangements. That is the golden rule, right there. The entire goal of Section 5 is saving lives and property by preventing dangerous touch voltages. When things go sideways, the system absolutely must recognize the fault and cut the power instantly, like before anyone even has a chance to get hurt. But how exactly does a static bundle of wires do that automatically? Okay, let's dive into this. Meet the MEN system, the multiple earth neutral. This is the absolute bedrock of electrical installations in our region. Instead of just kind of crossing our fingers and relying on one single path to the ground, the MEN system connects the neutral conductor to the earth at multiple points across the network. And crucially, it does this right at your main switchboard. It basically creates this incredibly robust, highly reliable framework that is just perfectly designed to catch and redirect any of those rogue currents. So here is our roadmap for today's explainer. We'll quickly cover 1. The purpose of earthing. 2. The MAN system explained. 3. Core components and sizing. 4. Equipotential bonding. And finally, 5. Earth fault loop impedance. All right, Section 1, the purpose of earthing, the escape route. Picture this. You're doing a normal load of laundry, but inside your metal washing machine, a live active wire has vibrated loose, and now it's directly touching the inside of the metal casing. So the outside of the washing machine is actually live. Let's contrast these two states. In normal operation, electricity flows safely through insulated cables, powers the motor, powers the pump, and returns nicely through the neutral wire. But in a fault condition, that rogue current is literally just sitting on the metal casing, waiting for a path to the earth. Without a designated, low-resistance escape route built right into the wiring, the moment a human touches that appliance, their body becomes the path to ground. And we definitely do not want that. Earthing provides that designated escape route, ensuring the current has an easier, much faster path to take that doesn't involve you. Which brings us to Section 2, the MEN system explained, building the network. To guarantee this escape route actually exists, the MEN system acts as this beautifully interconnected network. It's carefully designed so that a fault anywhere in the building has a direct highway straight back to the source to trip the breaker. According to Clause 5.3, we need some really specific, mandatory parts to physically build this out right now. We need the earth electrode, which gets driven deep into the soil. We need the main earthing conductor connecting the board to that electrode. We need the protective earthing conductors. Those are the green and yellow wires running out to your actual appliances. And finally, the MEN connection itself, linking the earth bar to the main neutral conductor right at the switchboard. Let's move to the next step and see how this builds, literally tracing the exact journey of a fault current through this network. So it starts at the exposed conductive part, our trusty metal washing machine. The current rushes down the protective earthing conductor in the wall, boom, arriving at the main switchboard. Here, the MEN link allows a massive surge of current to just dump into the neutral, instantly tripping that circuit breaker. And simultaneously, any excess potential gets directed down the main earthing conductor, safely dissipating out into the ground via the earth electrode. It's brilliant. Section 3, Core Components and Sizing, the Rules of Construction. Now, obviously, a safety net is only as good as the materials it's made from, right? Which is exactly why the standard dictates some really strict minimums. These components have to survive decades, hidden inside walls, up in ceilings, buried in damp soil, all without corroding or failing when you need them most. Now, what's really interesting about this slide is the dimensional differences in Table 5.2 based on material. A copper-clad or stainless steel rod, that only needs to be 12 millimeters thick. But if you decide to use hot-dipped galvanized steel, well, the standard requires a thicker 16mm circular rod. This perfectly illustrates how the standard is actively accounting for different electrical conductivity and corrosion resistance over long periods of time. But hey, it's not just about what the rod is made of, it's heavily about where you put it. The standard points out a very specific geographical compliance difference here. In Australia, the vertical electrode has to be driven down to a minimum depth of 1.2 meters. But in New Zealand, it must be 1.8 meters. Why the difference? Well, Clause 5.3.6.4 dictates the electrode absolutely must maintain effective contact with moist soil that isn't subject to excessive drying out. Deep, moist soil gives you that critical low resistance necessary to dissipate electrical energy safely away into the earth. Moving on to Section 4, Aquapotential Bonding, Water, Electricity, and High Risk. So, while we've been talking a lot about routing fault currents to trip a breaker, high-risk wet areas present an entirely different kind of hazard. We're talking about dangerous voltage differences. It is absolutely vital that we clearly distinguish between these two concepts. Earthing, as we said, is about creating that low-resistance highway to the ground to clear a fault. Equipotential bonding, on the other hand, that's about physically connecting various exposed conductive parts together. By linking them with a bonding conductor, you ensure they are all sitting at the exact same electrical potential, or voltage. Think about it. If two metal objects are at the exact same voltage, current literally cannot flow between them. Bonding basically ensures you don't accidentally become a human conductor bridging two metal objects at different voltages. And let me be clear, this is not optional in high-risk zones. The standard strictly mandates bonding for conductive water piping, structural metal in showers, swimming pools, and even certain conductive building materials. I mean, think about the extreme danger here. Climbing out of a swimming pool, dripping wet, and grabbing a metal pool ladder that just happens to have a slight voltage difference from the wet concrete you're currently standing on. Wet skin has drastically lower electrical resistance. Bonding ties the ladder and the reinforcing steel in the concrete together, completely equalizing the voltage and neutralizing that deadly risk. It's a lifesaver. Which brings us to our last stop, Section 5, Earth Fault Loop Impedance, the final check. Okay, so we've sized our components, right? We've bonded our wet areas. Now for the mathematical proof that our physical safety net will actually work fast enough when disaster strikes. First, we got to define the loop itself, which is designated as Z's. The Earth fault loop is the entire round-trip circuit that a fault current has to travel. I'm talking all the way from the supply transformer, down the active street wires, through your breaker to the faulty appliance, and then all the way back through the protective earthing conductor and the MEN connection. If there is too much resistance or impedance in this massive loop, the current just won't spike high enough, and your protective breaker simply will not trip fast enough to save a life. So to completely prevent a delayed trip, Clause 5.7.4 gives us a strict mathematical ceiling on resistance. And this brilliantly illustrates how math essentially guarantees human safety. The formula is the impedance of the loop, ZS, multiplied by the tripping current of the breaker, IA, must be less than or equal to the system voltage, UO. Let's break down these variables just a bit more so we can see how they interact in the real world. As we just said, ZS is the total impedance or resistance of our giant fault loop. IA is the specific amount of current required to force your specific circuit breaker to trip instantly. And UO is the nominal voltage of the system pushing all that current through. So, here's the catch. If your earthing wire is too thin, or maybe it's just way too long, ZS goes up. And if ZS goes up too high, the whole formula breaks, meaning that breaker won't trip in time. And here is the constant in that formula, 230. 230 volts is the nominal AC voltage to Earth in our region. So the crucial point is that your protective device must operate and cut the power way before this 230 volts is allowed to just sit on an exposed metal surface long enough to become lethal. The total resistance of your earth loop multiplied by the trip current can literally never exceed this 230 volt threshold. Which leaves us with this final, incredibly critical question. When you plug in an appliance, or touch a metal light switch, or step barefoot into a wet shower, is the impedance of your electrical safety net actually low enough to catch a rogue current before it's too late? You know, Section 5 of the AS NZS 3000-2018 isn't just some boring book of regulatory jargon. It is the literal anatomy of a lifesaver, meticulously designed to ensure that the answer to that question is always a resounding yes. Thanks for joining me on this explainer, and keep learning.